Hey everyone, we're going to do a quick review of concavity and the ways in which first and second derivatives affect the shape of a graph or curve. Then we're going to tackle a challenging but illustrative and comprehensive example. Remember that the graph of a function is concave down when the second derivative of the function is less than 0, it's negative, and that the graph of a function is concave up when the second derivative is greater than 0 or positive. Right? You see the couple of examples of each of the cases, right? One when the first derivative is positive, the other when the first derivative is negative. There is this sense of concave down, the curve is in a sense facing down or opened downward, whereas concave up curves are facing upwards or open upwards in a sense. And then we have an inflection point, which is a point on the curve, is illustrated right next to the definition, where the function changes concavity. It goes from being concave down to concave up or concave up to concave down. We call that point at which that occurs an inflection point. So note that the second derivative right there has to equal 0. Right? Or, I should say, or does not exist. It's also possible the second derivative does not exist. Just remember, these are the four curves that we consider, depending on the values of the first and second derivative. Those are the four curves that will determine the shape of our graph. So let's look at this example, which remember I said in class was way too complicated to go over. You can find this in Stewart in section 4.3. We're going to sketch the graph of this function right here. And in doing so, we're going to identify the usual first derivative information and then second derivative information. We're going to approach this the exact same way that we approach every other problem, right? We're going to start off by letting the first derivative equal 0. Now this time, because we have to use the product rule, we're going to have to do a little bit of simplification first, right? And before we even do that, we have to use product rule, right? First derivative, 2/3 x to the negative 1/3. Derivative of the first term, leave the second term alone. Plus the, right now we leave the first term alone. Take the derivative of the second term. And make sure to multiply by the derivative of the inside, which is negative 1. Right? Chain rule. Stuck a chain rule in there, right? Now, before we're going to let this equal 0, first I want to write this as fractions, right, with positive power. So we're going to get 2 times the quantity 6 minus x to the 1/3 over 3 x to the 1/3. And this is going to be plus, leave a little bit of space there, plus x to the 2/3 over 3 times 6 minus x to the 2/3, and then times negative 1. So actually, let's go ahead and make that a minus, right, because of that negative 1 right there. And now at this point, remember, we're going to want this to equal 0. So before we do that, why not make this one fraction, which means get a common denominator going. And you can be a little bit clever here and do it. And believe it or not, this is going to simplify the final answer by quite a bit. After you do a bit of simplification, you're going to wind up getting 4 minus x all over x to the 1/3, 6 minus x to the 2/3. If you have questions about that, then please ask me tomorrow or the next class. And that's what we're going to set equal to 0. Now, there are two important points to make right here. Number one, f prime of x equals 0 at x equals 4, right? Because remember, you can't divide by a number and get 0. However, we also have f prime does not exist at x equals 0 and 6. At 0, we're dividing by 0. At 6, we're also dividing by 0. That's a little off the beaten path, right? Remember that a critical number is where the derivative equals 0 or does not exist. So the one thing I'm going to write down here, I'm not going to get into the intervals of increase, decrease. I'm not going to get into local max and min. I'm going to save that for when we do the chart a little bit further below. But what we do have is that f has critical points. For 2 to the 5/3, that's what you get when you plug 4 into your original function, highlighted in yellow up there. 0, 0, right? Note that if you plug 0 into f, you get 0 times 6 to the 1/3, that's 0. And then you also have the point 6, 0, right? Because if you plug 6 into f, you get 6 to the 2/3 times 0. Okay? So we took care of the critical points, right? All right, now I'm going to switch to green ink because we're looking at the second derivative. Again, I'm going to save the intervals of increase and decrease and local maxes and mins for a little bit later. Now, at this point, you're just going to have to believe me because I'm not getting into taking the second derivative and simplifying it and all that nonsense. Stuart takes the same approach. He doesn't bother, deriving all of it. But trust me, that's the second derivative. And one interesting thing to note about this is that the second derivative does not equal 0 because the numerator never equals 0. However, we should still note that f prime does, that's f double prime right there, does not exist at x equals 0 or 6. Which we should expect, because if the first derivative doesn't exist at 0 or 6, then the second derivative, sure as shoot, is not going to. Okay, so now let's draw our interval line. I'm going to line it up like this. I'm going to put f prime up here, f double prime down there. Write it out like this. Maybe I'll make this 0. I'm actually going to draw it through the top and the bottom because 0 is a special number for both of them. 6, same thing. And then up here, I'm also going to include the number 4. Okay, so we've got those those three values, 2 of them which apply to both derivatives, right? Okay, and we're just going to test by plugging in points. Now I'm going to use the orange ink to denote that we're plugging into the first derivative, which is this. Well, it turns out when you do this, and you can test this out, you're going to get a negative value, positive, negative, and negative. That's a little bit different. You might expect them to alternate every time, but they don't, right? You have a negative, then another negative. Just to see that, right, if you plug in the number 5, you're getting a negative numerator right up here. This is going to be positive, and this is going to be positive. So you have a negative divided by a positive times a positive, which is negative. Similarly, you plug in a number like 7, the numerator is still going to be negative, and the denominator is still going to be positive. Okay? Anyway, switching to green, because of the second derivative, the second derivative winds up being negative, right? The numerator is always negative. Plug a negative number into x to the 4/3, it's positive. Plug it in here, you get another positive. So a negative divided by a positive denominator is negative. Okay, and then it turns out the second derivative remains negative if you plug in a value from 0 to 6. And only at the very end does it become positive. So now that we have this, I want to write my summary right on the left side here. So let's just say, so f is increasing on the interval 0 to 4 and decreasing on negative infinity to 0, union 4 to 6, union 6 to infinity. Don't just write 4 to infinity because it's not decreasing at 6. Its derivative is 0 there. Also, f has local min f of 0 equals 0, and local max f of 4 equals 2 to the 5/3. Right. So now moving on to the second derivative part. I'll skip a little bit right there. By the way, just to point out, we nailed that and that. Now for the second derivative stuff, f is concave up on 6 to infinity and concave down on negative infinity to 0, union 0 to 6. Also, f has 1 point of inflection. I should say an inflection point. Six comma 0. Note that 0, 0 is not an inflection point because the second derivative is negative and then continues to be negative afterwards. So it does not, f does not change concavity there. So 0, 0 is not an inflection point. All right, and so we did that. And so now we can sketch the curve. And note that the way I just lined up my curve right now, I lined it up underneath the interval so that I can mark these important x values on the curve just a little bit easier. You don't have to do it this way, I just think it's a little bit nicer. Maybe space the 4 a little bit further from 6, maybe a little bit more here and here. Okay. So anyway, we've got our critical points. Those are going to be pretty important, right? Because those are the only points that we have on the graph. Right? So just to point out, I'm going to actually sketch this in green just to emphasize, right? We've got this point right here, this point right here, and I guess we've got this point right here, right? This is 2 to the 5/3. Okay? And if we sketch the curve based on our interval chart, well, we know that this first part right here is something like this, right? It comes down. Then it's going to actually go back up, right? Because we've got a plus over a minus between 0 to 4. Then a minus over a minus. We're going to keep going down. Well, let's try that a little bit better. Keep going down. And this is a little bit unusual. We're actually going to continue doing something like that. Right? We're going down, but more slowly. So right here, this is not something we're used to seeing, but we actually have a vertical tangent line right here. That's why the derivative doesn't exist there. And right here, I think it's a little bit more obvious. We've got a cusp. Right, but the vertical tangent line, that's not something we see all that often. Okay, and this is the curve y equals f of x. So that's how you get your sketch.